In this video, we're going to continue working with section 3.4. So if you recall, we talked about elasticity of demand, and we started with a couple of formulas. And if you look, just remember we wrote down this formula here where epsilon of the price is going to equal negative P over Q times the derivative of Q. And remember, Q represents the demand, and P is going to represent the price. So what we're going to do is we're going to use that formula, and then remember we talked about in class last time the theorems and the different conclusions you can make. So we're going to use that, and we're going to try these practice problems. So the first thing is we're asked to find the elasticity, so that means we're going to use the formula. So the formula for elasticity. So for part A, I'm going to use epsilon of P is equal to negative P over Q times the derivative of Q. So before I start plugging in, off to the side here, I'm going to go ahead and I'm going to find the derivative of Q. So I have Q is equal to 500 minus P, and that'll always be given to you. So the derivative of that is just going to be negative 1. So then I'm going to take that, and that's going to get plugged into this formula here. So for epsilon of P, it's going to be negative P over Q, so over that entire formula, times the derivative of Q. So the derivative of Q is negative 1. So then from here, I'm going to go ahead and I'm going to simplify this expression. So I have epsilon of P is equal to, so this is negative P up top, so negative P times negative 1 is going to be P over 500 minus P. And keep in mind that negative doesn't necessarily have to be in the numerator. It can be in the denominator, or it could be out in front. You just need one negative in the fraction. So here's my formula for part A. So then for part B, it says the elasticity at the given price and state whether the demand is elastic or inelastic. So this is where we're going to make our conclusion. So for part B, the given price is 38. So I'm going to plug in 38 into my function. So it's going to be 38 over 500 minus 38. So we plug in, so that's going to be 38 over 462. You divide that, and you're going to get a decimal. So 0.082251. So basically, I'm getting a number that's less than 1. So since I'm getting a number that's between 0 and 1, so less than 1, between 0 and 1, that means that my elasticity function is considered at this price an inelastic situation. So we call the demand inelastic. So I'm going to just kind of write that. So since my epsilon value here is in between 0 and 1, that means the demand is inelastic. And remember, the way that I thought of that is it's not elastic because it's a really small number, so it's not stretching much. So what that means, so to conclude from that, as price increases, the revenue will also increase, or vice versa. So if price decreases, well, then revenue is going to decrease. So that is going to be, I basically just looked up in my chart here to make that conclusion. So I got inelastic, and then since revenue is, or price will increase when revenue, if price increases, then revenue will increase as well. So that's the conclusion part. And then for part C, whenever you're trying to find a maximum, there's two ways to find when the revenue is a maximum. You could actually find the revenue formula, take the derivative of it, set it equal to 0, get your critical values. But the shortcut is going to be if you set epsilon equal to 1. because whenever epsilon equals 1, this is called the unit elastic, and this means that our function is being maximized, which our revenue is being maximized. It's unaffected, so that means that it's going to be maximized at that point. So, and if you look, it's when the derivative of the revenue function equals 0. So if you're trying to find a maximum, we're just going to set epsilon equal to 1 and solve for the price. Because we're trying to find the price that will do that. So I'm going to kind of write this out on what I just said. So set epsilon equal to 1 and solve for P to find the max. But I'm going to also say we could, so otherwise, use old method with the revenue function and find critical values. So when I say old method, I mean find the revenue function, which is just going to be your price times your demand. So find your revenue function, take the derivative of it, set it equal to 0, and get those critical values. So find critical values. So that would be the old way. That way is a little bit longer, especially in a problem like this, because we already have the epsilon formula. So I'm going to go with the new method, which is a little bit quicker, and it only works with this whole elasticity type of formula. So if I look at my elasticity function, so I have E of P equals P over 500 minus P. I'm going to set that equal to 1. So I'm going to have 1 equals P over 500 minus P. And then from here, I'm going to solve for P. So I'm going to put this over 1 and just cross multiply. So I get 500 minus P equals P. And then go ahead and add P to both sides. So I get 500 equals 2P. Divide both sides by 2. So we get 250 equals the price. So what that means is the price that would maximize the revenue would be $250. I'm going to just rewrite that so it looks like a 5. So we're going to go ahead and we're going to continue this. So let's go ahead and try this for the other examples on the back. So same process. So if we look at this, we're going to do all 3 parts. So the first part is going to be coming up with that elasticity function. So E of P is going to equal negative P over Q times the derivative of Q. So first part here, let's go ahead and find the derivative of Q. So when I look at Q, I notice I want to rewrite that because I don't want to have to do quotient rule. So I'm just going to rewrite that using a negative exponent. So this is just a rewrite. And then from there, I'm going to find my derivative. So negative 1 times 3,000, so negative 3,000 P, subtract 1, so I get negative 2. And then I'm just going to rewrite this so that it's not using a negative exponent. So my derivative is going to be negative 3,000 over P squared. So that's what I'm going to plug into my formula. So then over on this side, I have my epsilon of P is negative P over Q. So 3,000 over P times the derivative here. So I have negative 3,000 over P squared. And now we got to simplify this. So if we look at this first fraction here, so you're taking a P and you're dividing it by a fraction. So let's go ahead and simplify that. So that's going to end up being, so if you remember, maybe you've heard of the saying keep, change, flip. So whenever you're dividing fractions, if you just think of it as keep the numerator, change the sign of multiplication and flip the denominator, and then you'll just multiply. So this is really P over 1, and then times 3,000, and then P squared. So what ends up happening now is you have a P squared and you have two P's up top. So those are going to all cancel. The 3,000s cancel. So what you end up with is a -1 times a -1, which is going to end up being positive. So in this case, my elasticity function ends up just equaling 1. So what that tells us is that for all values of P, the price is going to, or the revenue is going to remain unchanged. So basically the revenue is maximized for all values of P. It's not going to change. So if we go ahead and we look at interpreting this by putting in, so for part B, plugging in a price, you're going to see that it's not going to change. So if I plug in 60, well, it's not going to do anything. It's just going to keep it as 1. So since we have this function here, since this function is equaling 1, it's the unit elastic, so that tells us that the revenue is unaffected. So that's why you're seeing 1 again. So let's just make a note of that. So since epsilon equals 1, the demand is the unit elastic, and the revenue is unaffected by a change in price. So it doesn't matter what number I plug in, I'm always going to get 1. So that kind of goes, this description kind of goes hand in hand with both of these. So then the last part for C is to find the price where it's maximized. Well, if we're trying to find the max, remember that's where you're going to set epsilon equal to 1. Well, epsilon already equals 1. So since, I'm going to put this in parentheses, set epsilon equal to 1, that's what you normally do, and then you solve for P. But since epsilon of any price is equal to 1, the revenue is maximized for any or for all values of P. So that's kind of like the exception to the rule. It's not really doing anything for us. So then the last scenario here, we are going to start again with part A. So part A is going to be to find our elasticity function. So we have negative P over Q times the derivative of Q. So off to the side, I'm going to rewrite Q. So let's do a rewrite first, because we don't want to have to do, well, the only way we know how to deal with a square root is if we rewrite it using fractional exponents. So this is going to be to the 1/2. And then what I can do is apply chain rule to this. So it's going to be 1/2 300 minus P, subtract 1 from that. So you're going to get negative 1/2 times the derivative of the inside. Don't forget about that derivative of the inside. So it's going to be times a -1. So that means Q prime is going to be 1/2, or actually let me go ahead and multiply that negative. So it's going to be negative 1/2. And then the inside's just going to stay because that's attached to the negative 1/2. The negative 1/2 exponent. So then before I go to plug this in, let me actually rewrite this so that we're not thinking of this with fractional exponents. So really what this is negative 1/2 square root of 300 minus P, because the negative 1/2 means the square root's in the bottom, and then the 2 I'm just putting at the bottom. So there's my derivative. So now I can go ahead and plug that in. So for epsilon of P, it's going to be negative P over 300 minus P times this whole thing. So negative 1 over 2 times the square root of 300 minus P. So now when I go to simplify this, this is actually going to become a pretty nice looking fraction because negative times a negative is going to make it positive. So I'm going to have positive P. On the bottom, I'm going to have the 2 out in front, but when you square a square root or you multiply a square root by itself, so it's the same thing underneath, we're just going to end up with 300 minus P. We're going to be left with what's underneath the square root. So there's my epsilon function. Now you can distribute that too as well, but we can do that later. It doesn't really make a difference. So there's my function. So now when we go to do part B, we're going to plug in our price of 250. So I'm going to plug that right into the function. So I'm getting 250 over 2 times 50. So 250 over 100. And we're getting 2.5 for that, which is greater than 0. So since this is a bigger number, think about this as it's elastic, it's stretching. So the demand is elastic, which means that the price and revenue will do the opposite. So if you're increasing price, the revenue is going to decrease and vice versa because it's a far stretch between the two. So since epsilon is greater than 1, the demand is elastic and an increase in price will cause revenue to decrease, or vice versa. So there are all of the different scenarios, and the last thing we have to do for this problem is we just have to look at finding the maximum. So you've seen a situation where you've come up with each of the inelastic, elastic, and then the unit elastic. So now the last thing is just to do part C, which is to find the max. So we're going to set epsilon equal to 1 and solve. So I'm just going to label this find max. So I'm setting epsilon equal to 1. So my function here, I'm going to go ahead and set that equal to 1 and then solve for P. So we can go ahead and let's distribute the bottom there. So it's going to be P. So we have 600 minus 2P. Then I'm going to put this over 1, cross multiply. So I end up with P equals 600 minus 2P. Bring the 2P over. So 3P equals 600. Divide by 3P. So you get the price equals 200. So that means in order to maximize revenue, the price has to be set to 200. And remember, keep in mind that you could have also done this using the revenue function. So you could have came up with the revenue function, which just means multiply P times the demand. And then from there, you would take the derivative, set that equal to 0, and then solve. So that would be a little bit more work because the derivative would get a little bit messier, but you would end up with the same answer. So take the derivative of revenue, set it equal to 0, and you would end up with your one critical value being 200, and that's the one that you would be keeping. So that's the process. I highly recommend just doing the elasticity function, setting that equal to 1 and solving it that way.